Hello and welcome to The Space Above Us, Episode 28, the Apollo Command and Service Module. Last time, we took a whirlwind tour of some of the computers and software that drove the Apollo program. From the triply redundant launch vehicle digital computer that kept the Saturn booster on track, to the LOL memory-powered Apollo guidance computer. These intricate machines served as the brains for their respective vehicles and guided them with remarkable accuracy through the void of deep space. While we only touched on one part of its story, the Apollo guidance computer will be drifting in and out of our narrative for quite a while to come. And if the phrase 1202 program alarm means anything to you, you know that it will be making a dramatic comeback a few episodes down the line. Today, we'll be talking about the vehicle that the AGC controlled, the Apollo Command and Service Module, or CSM. The Apollo CSM actually predates the Apollo program itself to an extent. Back in the late 50s, when the moon landing was nothing but a vague goal that might happen by the end of the 1970s, NASA engineers were already kicking around ideas for what would follow Project Mercury. We've covered this in more detail in episode 24, so I won't belabor the point, but let's take a quick look at how this spacecraft came to be. When NASA sets out to make a new spacecraft, they don't really just sit down and start cranking out blueprints. That's not how government procurement works. What they really do is start figuring out, in extensive detail, the goals and capabilities of their proposed vehicle. Now, this is sort of a fine line since these requirements can be so fine-grained they may as well be blueprints. And NASA engineers do have a lot of input and oversight into how the contractors eventually implement the concept of the spacecraft. But it all starts with some broad goals. The vehicle that would go on to become Apollo was to support a crew of 3 on 2-week missions, be capable of flight in cislunar space, the region between the Earth and the Moon, and was to be ready to fly sometime around the mid-60s. Once President Kennedy set our sights on the Moon, the task became a lot more concrete, and with it, the requirements. The maximum weight became more well known as it became apparent what boosters would be available to support the flight. The capabilities of the onboard computer crystallized to the point that work could begin on it right away. And even with our small amount of spaceflight experience with the early Mercury flights, requirements related to things like thermal protection, environmental control, and other subsystems like that became a little more well understood. Once NASA had figured out the high-level concept of what will be required, they met with representatives from the aerospace industry to show what they had in mind and see who was interested in bidding on the project. This was a high-stakes and high-prestige contract, and a lot of companies were interested. A lot. When NASA held their initial Apollo Technical Conference in July of 1961, representatives from over 300 companies showed up to see what was going on. By October, the list was down to 5 of the biggest aerospace companies in the country: Martin, General Dynamics, North American Aviation, General Electric, and McDonnell, who created the Mercury and Gemini vehicles. The bids by these companies were no joke. When you're angling to build a new spaceship for NASA, you don't just sketch it out in the back of a napkin. All of these companies had already begun work on their bids years ago, based on the mere rumor of a possible future moonship. Teams of dozens or hundreds of engineers worked long hours for weeks and months, spending millions of dollars of company money just for the chance of building the Apollo spacecraft. For some of these companies, it would have been a make-or-break decision. The bid process was so involved and so expensive that failing to land the gig could spell the end of the company. For this reason, several of them paired up to bid as a team. For instance, Grumman Aircraft chose to bid as a subcontractor with General Electric and several other companies, rather than bet the company on such a shaky contract. For a great inside view of what this process was like, I highly recommend the book Angle of Attack by Mike Gray. It follows the fascinating story of North American Aviation's bid for not only the Apollo spacecraft itself, but the S2 stage of the Saturn V rocket as well. It also gives a glimpse into some of the forceful personalities that made the Apollo program a reality, such as the head of North American Aviation Space Division, Harrison "Stormy" Storms. If you're wondering why someone decided to write a book about the bid process of North American Aviation and not the other companies, That's because on November 28, 1961, it was announced that they had won the contract to build the Apollo spacecraft, humanity's first moonship. They had also landed the S-2 contract, which meant that the men and women at their space division in Downey, California, were going to be quite busy for the next few years. North American Aviation's main business, like most of these companies, was creating aircraft for the military. Some of their notable achievements were the P-51 Mustang, the B-25 bomber, the F-86 Sabre fighter jet, and the T-6 trainer airplane, which many British pilots cut their piloting teeth on in World War II. They were also responsible for a little project you may have heard of, the X-15 rocket plane. North American had a tricky task ahead of them. The Apollo spacecraft came with reams of requirements, but some were surprisingly poorly defined, all things considered. And not all the requirements were official requirements. For example, during the bidding process, several industry proposals included lifting body vehicles rather than the familiar blunt cone used in Project Mercury. These would be more complicated to build, but would provide more control authority during re-entry and landing. But legendary Apollo engineer Max Faget had a strong preference for blunt face cones and forcefully suggested that companies consider that in their design. Perhaps most critically, the mode debate had not yet been settled at this time. Lunar Orbit Rendezvous wouldn't be chosen until July 1962, so North American started working on elements that would likely be the same no matter what, such as environmental control systems, while hoping that NASA would figure out exactly what their spacecraft should do, and soon. North American actually fought against LOR strenuously in the lead-up to the decision. I'm sure that they would tell you that it just didn't line up technically, but I think it's pretty obvious that the real reason was that suddenly their spacecraft would not land on the moon. That's quite a blow to such a prestigious project. To try to make up for the LOR decision, North American planned to bid on the lunar lander, claiming that it would simplify the engineering to build the whole spacecraft under one roof. But that was just too big of a contract for one company, and NASA eventually had to ask them not to bid. With the mode chosen, all the parts fell into place and detailed designs could really be made. The Apollo spacecraft was now 3 spacecraft. The new lunar module, which would actually land on the moon, the conical command module, which would house the crew and was the only part of the spacecraft to return to Earth in one piece, and the cylindrical service module, which included resources and the main propulsion system. Let's start with the service module. The idea here was that a 2-week trip to the moon and back was going to require a lot of resources and rocket engines that didn't really need to come back to Earth. The smaller you can make the re-entry vehicle, the better. So most things that didn't need to come back were placed in a large disposable cylinder called the service module. It's a pretty similar idea to the equipment and retro modules on the Gemini spacecraft. The main cylinder of the service module was about 25 feet tall and 35 feet wide. Extending below the main cylinder was the most visually striking feature of the service module, the large engine bell that was part of the Service Propulsion System, or SPS. Just to compare this engine to something we already have some experience with, the engine on the Agena target vehicle from Project Gemini produced about 70 kilonewtons of thrust. The SPS produced about 90 kilonewtons. If this giant engine seems like a bit much, you're not wrong. Since North American was originally planning on landing the whole spacecraft on the moon, they chose a big engine. And since engines need to be locked down early, they didn't bother changing it once it became clear that this was not going to be the case. The interior of the service module was split into several bays. Imagine a pie cut into 6 slices, but with a circular 7th slice in the center. The center slice, a cylinder within the larger cylinder, housed high-pressure helium tanks used to pressurize the propellant tanks for the SPS. The propellants, a hypergolic pair composed of kerosene and nitrogen tetroxide, were stored in large tanks in the outer bays. Despite the SM being powered by hypergolic propellants, there were also large tanks of hydrogen and oxygen, which were used to power the fuel cells, which in turn provided electricity for the entire spacecraft. There were 2 tanks each of hydrogen and oxygen. I wonder if we'll be hearing about O2 Tank 2 at any point in the future. I suppose I shouldn't stir up speculation. On the outside of the service module were several sets of small thrusters used for attitude control, as well as a high-gain antenna to ensure stable communications from the moon. All of these various tanks and thrusters and fuel cells were carefully arranged to maintain a strict center of gravity. Sitting atop the service module is the heart of the entire mission, the command module. The CM was a large cone that was just under 11 feet tall and just under 13 feet wide at the base. For scale, if you added up the diameter of the Mercury spacecraft and the diameter of the Gemini spacecraft, you'd be just a few inches shy of the diameter of the Apollo command module. It was big. Covering the base of the CM was the all-important heat shield. Similar to Mercury and Gemini, the heat shield was made of an ablative compound that would burn off as the vehicle ripped through the upper atmosphere. The burning fragments would carry excess heat and energy away from the spacecraft. This heat shield would have to withstand forces in excess of its predecessors, since Apollo would be entering the atmosphere at much higher speeds. Orbital velocity is absurdly fast, but at 17,500 miles per hour, it was a piece of cake compared to the roughly 25,000 miles per hour Apollo would be returning at. In the absence of an extended test program or advanced computer simulations, engineers overbuilt the shield a bit to keep things on the safe side. Upon later analysis, it became apparent that they actually could have shaved a couple inches and several hundred pounds of material away and still be fine. Better safe than toast. Moving up from the base, we reach the shiny metallic exterior of the main vehicle. Embedded within it is a large hatch, 5 windows, 12 reaction control system thrusters, and a small opening for optical instruments used for navigation. On the top was a clever structure that allowed the CM to dock with the lunar module, but then be removed from the inside by the astronauts, allowing them to pass through to the LEM via a short pressurized tunnel. Underneath the shiny exterior skin, you would find the pressurized shell that contained the main interior of the vehicle. This structure could best be described as an angular igloo with a hat on it. Well, probably not best described, but it certainly could be described that way, and that's what I'm going with. One thing of note here is that with Apollo, we have returned to the Mercury style of spacecraft integration. One of the lessons learned on Mercury was that it was a real hassle having to remove 8 other unrelated parts just to access the one thing that was having an issue. Because of that, Gemini favored a modular design, with as many systems as possible placed between the exterior skin of the vehicle and the interior pressurized volume. This allowed engineers to simply remove exterior panels and easily access modular systems. But since Apollo construction actually started well before Gemini flew, this lesson wasn't carried forward. Though in retrospect, given the margins available and the imposed schedule, it's somewhat likely that it wouldn't have been possible anyway. If you were to open the hatch, not in space please, the first thing you would see is a fiberglass chair that the lunar module pilot would sit in. Peering inside, you'd see that similar chairs were on either side for the commander and command module pilot. For reasons that are unclear to me, these were called couches. The 3 couches were held in place by several structural beams, keeping them right in front of an extensive control panel. I don't know what the collective noun for control switches is, but I'm going to go with a bewilderment of switches. Including circuit breakers, communications equipment, mode selectors, a state-of-the-art computer, there were 566 switches in total. In addition, there were 40 different indicators and 71 lights designed to convey various states of the spacecraft. The control panel spread across the entire width of the vehicle in front of all 3 astronauts, and partially surrounded them on the sides. The SCE switch is over on the right on panel C, bottom row, near the middle. Keep that in mind for Apollo 12. Using these extensive panels and the incredibly capable Apollo guidance computer, the crew could control all aspects of their spaceship from launch, coast, lunar orbit, and eventual splashdown. Connecting it to everything else, and all those parts to each other, was 15 miles of wiring. which is enough for about 50 typical two-bedroom homes, at least typical for the 1960s. Though the main control panel and the crew couches are the parts most often portrayed in movies and documentaries, there was a surprising amount of extra volume in the Apollo command module. In fact, out of 366 cubic feet of pressurized volume, 218 were usable by the crew. For context, I looked up my car's interior volume and found it to be about 100 cubic feet, including storage areas. Beneath the main control area was the lower equipment bay. Here you would find the specialized navigation equipment, which was surprisingly similar to the sextants of old, storage compartments, and the tunnel to the lunar module. The navigation equipment was mounted to the side of the spacecraft, and its optical elements passed through the wall, allowing astronauts to spot specifically chosen navigation stars. Using the specialized equipment, they could indicate where the star was, allowing the guidance computer to update its current state vector and correct any slight errors that may have built up over time. The command module and service module combined together Voltron-like to form what was called the CSM. Remember how I mentioned that North American Aviation was forced to begin construction of the command module before all the requirements were fully known? Because of this, engineers were plagued by a never-ending stream of change requests. Sometimes a change was necessary because the requirements changed. Sometimes an astronaut wanted the switch put in a different place. Sometimes someone figured out how to do something better, or any number of other reasons. Whatever the reason, at one point something like 1,000 change requests a month were flowing down to the factory floor. And as any engineer can tell you, trying to work in an environment with ever-shifting requirements is a nightmare. To try to gain a modicum of control over these changes, the command module was eventually split into two versions, Block 1 and Block 2. Most new changes would be applied to Block 2 only, allowing work to continue on Block 1 without interruption. The only catch was, the two versions were really significantly different. Block 1 lacked the equipment necessary for rendezvous with the lunar module or flying to the moon. As such, it was only to be used in Earth orbital flights, while Block 2 would fly the actual missions. You may be wondering, as I sure did, why they even bothered continuing with Block 1 at all. To be fair, there were some pretty good reasons. Even if Block 1 and Block 2 differed significantly, they were still more similar than Gemini or Mercury. So, astronauts could begin to get accustomed to their slick new ride. Additionally, plenty of stuff would be similar, if not identical, for Earth orbital and lunar flights. Hand controllers, crew couches, environmental controls, general crew cabin layout, all of that stuff could get a good shakedown. Block 1 was to be used for some uncrewed tests, as well as at least Apollo 1 and Apollo 2. As we will learn in a few weeks, that would never come to pass. Compared to Gemini or Mercury, the CSM was an absolute beast in every respect. Size, rocket power, brain power, crew accommodations, and overall capability. Just the command module on its own, let alone the service module, strikes an imposing figure when placed next to its predecessors. But with lunar orbit rendezvous as the chosen mode, it would not be able to accomplish Kennedy's goal on its own. The CSM needed a partner, something specialized and light, something that would take two brave astronauts from lunar orbit down to the surface and back to the mothership again, never seeing an atmosphere along the way. Something never seen before. The world's first true human spaceship. It needed the subject of our next episode, the Apollo Lunar Module. Ad Astra. Catch you on the next pass.